Ladies and gentlemen, welcome to Chapter 8 again. We're going to talk about our old reaction that we spent the whole day on Monday. And remember I said sometimes to predict the product involves 3 questions instead of 2. Our activity on Monday, we only had to do 2 questions. And question 1 was, which HX forms fastest? You don't have to worry about that one here. There's only one HX, HBr. The next question was, which CH breaks first? I'd like to point out with my particular example here, that question doesn't matter either because both products come from the same H being removed. You must find the H that needs to be removed and describe it to me with a category. Which H bonded to carbon is the easiest to remove from this molecule, and you won't find the right energy unless you know the right category. So tell me which H in this molecule is the easiest one to remove. The tertiary one, and it's not just because it's tertiary, it's also special in a second way. What's the second way? The category is not straight tertiary because that will get you the wrong number from my table. I promise. It's tertiary and it's what do you call the carbon that's one away from an alkene? There's 2 of them in this molecule, and they're both called allylic. It's based on the allyl group, which you know. What is an allyl group? It's a vinyl with an extra C. The extra C is called the allylic carbon, and this thing has a tertiary allylic. And I'd like to remind you that both of those products have that H missing. There's no H on this carbon. I hope you agree. There's also no H on this carbon. So the first 2 questions from last lecture are answered already for you here. So which HX forms fastest? We don't care. There's only one HX here. Which CH bond breaks fastest? We don't care. There's only one CH bond breaking here. Question 3. Which CX, he writes H when he says X, that's weird. Which CX bond happens fastest? Happens fastest. We're going to do some research. And what I'm going to do is stop my share and pop. All right, everybody, we're back. We are going to go to Starboard. The information we need is on this document, which I shrunk down a little too severely. Got it straight from test 3. This is mostly a test 3 practice item, okay? Every other semester, this is test 3, okay? Every time you see that table on an exam, that means you're going to find these questions in Chapter 8 on test 3. So I need numbers from this table. How about HBr since it's over here? Question 1, is it going to be a negative number or a positive number? Because that's a new bond. Negative. And what's the actual number? Is it negative 368? This one is secondary allylic, everybody. This one is tertiary allylic. CBr, they're new bonds, they're negative again. Put them in blue. CBr, there's our 2 numbers. Negative 228 for secondary. Negative 224. There's your numbers I'm asking about here. Which one's faster? More exothermic. Thank you. I guess that's the answer to the second part of this activity. We'll explain later. I mean, you can say because it has a more exothermic energy, but I want you to explain why based on stability. Okay? We'll do that later. So my major product is here. That is probably not something you would have intuitively predicted. Your decision's based solely on faster versus slower, everybody. Okay. Usually we're going for tertiary over secondary, aren't we? Okay, what about BRBR? Oh, you're breaking that bond. So what's your sign? Positive. And it's 192. It's over here. And negative 368 was here. What else? We got, what about tertiary allylic CH? I've been doing this so many years, I think it's 354. And yes, it's this one here. We'll put it in red. Okay, good. We need these numbers later. Well, we don't even need these numbers. Yes, we do. We needed to do this prediction we just did. Give a mechanism. It doesn't say cal. I wasted a lot of time. So let's make it not a waste of time. C. Since we're doing it. Calculate delta H prop 1. I mean, we did it the other day. Prop 2. And delta H RXN. Major product only. All right, that kind of makes it like Monday again. And we're going to finally do part A. Do you remember what happens during initiation? Initiation. What happens? You break the BRBR, exactly. And I'm just going to short form that to init. The heat is what does this. Hook. Hook. You get 2 BR radical. Okay? And that's what H nu is for. Oh, H nu. What's H nu stand for? What is that? What the heck? That doesn't look like heat. Heat is only one form of H nu. H nu is Planck's constant times the frequency of the radiation. It's the energy of the radiation when you multiply those two. And radiation can be heat, light, ultraviolet, gamma, radio, micro, beta, alpha. A lot of radiations, right? In this experiment, it's only, it's usually, okay, it's always heat or light, one of those two. You don't need those extreme energies like gamma, and you don't need the weak energies like radio. Prop 1. Yes. Yes. Say it again. 357 for breaking a secondary allylic CH bond. No, this is tertiary. It's got 3 carbons attached to it, right? 3 carbons attached. 1, 2, 3. Over here? No, there's nothing going on over here. I'm not doing any bond there. Yeah, but I already counted for that as negative 228 for secondary allylic CBr. Is that what you're saying? Oh, you're worried about where this radical came from. You're not. She's not worried about that at all. Maybe she will be after I explain. But
I was saying for the tertiary allylic for the BR.
This position here is secondary allylic. This is tertiary allylic for the BR.
From the number chart. Where you got the numbers?
The number chart, yeah. Did I get them wrong? Wait, for BR, no, BRs are here.
Okay, now look at the first one.
This one?
No.
This one?
Yeah, I thought it would be the one above it.
Well, you didn't break the one above it ever. You never broke that bond.
So what is that?
I mean, that would be this bond over here, if you want to know. That would be 357, but we're not talking about that carbon at all today here, are we? Name that secondary allylic.
No, the CH, methyl, primary, secondary.
Oh, yeah, methyl, primary, secondary, tertiary, vinyl. Vinyl, you'll never break in this question ever. If you did, you messed up. Because those numbers are way too high. We always break lower numbers, right? And then there we go. And we got prop 1. You got to take the Br radical you made and grab the H. Which H? The one on the tertiary allylic position over there. And they're going to hook up. This is what we call a hookup mechanism right here. It's not that kind of hookup, ladies and gentlemen. HBr is made. And your famous carbon radical that's tertiary allylic, a very nice carbon radical by the way. And can we do prop 2 immediately for the minor product since we're here? Prop 1, and then prop 1 is for both products. And for the minor, prop 2, minor, it's here. You take this guy and you need to have the radical instead of there, you need it to be here before you can do prop 2. Radical is where the Br goes. Tell me what the name of that transformation is. Sorry, say it again. No, hydrogens are all in the same position beginning and end. So it's not a rearrangement of any kind. There's no atoms moving at all. So it's not a reaction. That's what I was hinting at. Atoms in the reactant are in exactly the same places for atoms in the product. That is not a reaction, but electrons are moving. What do you call it when a species has electrons moving around within the species? Resonance. Now I need a mechanism for your resonance. Where did that new pi bond come from? What 2 electrons combined to make the new pi bond? I am talking about this pi bond, the new pi bond. Where are the 2 electrons coming from? One from the radical. So a radical goes in between the atom. Where's the second electron come from? From the pi. And where does the radical come from for the carbon? Also from the pi. It splits in half. That's a terrible hook. That's still a terrible hook. Starts on the pi, ends at the atom, and it's a hook. 3 hooks. This is resonance. Just a reminder, it's a resonance. Now you can do prop 2. You have the radical in the right position to make the indicated major product. Let's do the hookup. The hookup says Br will react like this. And create 2 species. You're going to get your desired major product. And what other species do you make? What other species is made with those hooks? The Br what? Radical. That's what you must use in the next step. Oh, that is, wait, we're finished. That prop 2 is done. Prop 1 is the same for both. Prop 2 for the other product is just the unresonated version of the same radical. How do you know? Look at the product. This becomes this with a direct hookup. Just like this became that with a direct hookup. This could not become this with a direct hookup. You needed to resonate first. So prop 2, that's major, by the way. I misspoke. prop 2 major, and prop 2 minor is the unresonated radical. I didn't leave enough room, did I? There. And we got a radical and a methyl and BRBR hooking up. So we better know the hookup mechanism. One hook from one species, the other hook from the middle of the bond of the other species, and the other half goes to the BR. Number one mistake I see is those hooks not starting on bonds. For some reason, students just forget that and they start at a nucleus. That is not a good thing to do. Starting any arrows or hooks at a nucleus, that is not where electrons are. You have to lose points. So both of those hooks right here, starting on the bond. This hook ending at the other hook, making a bond. That's a CBR bond. And we're gonna get our major product here. I lost my double bond, I apologize. I got it back. I don't know how that happened. These things happen. And what's the other product again? BR dot. Okay, put a little line between these guys so you keep them separate. There you go. Delta H, prop 1, prop 2. We got all the numbers we need on the screen if we shrink things just a little. Breaking BR, CH is here. That's plus 354. Plus 354. What about making HBr? What kind of number you get there? Negative 368. Delta H P1 for both reactions. Positive 354 minus 368. Exothermic to the tune of negative 14. Kilojoules per mole. That's major and minor. Major and minor. Delta HP2 looks like I have on the left the minor. Minor equals you're breaking BRBR. How much? How much energy to break open BRBR? Positive 192. How much energy do you get back when you make the the tertiary allylic CBR? Negative 224. And I'm just doing the reverse in my head. 4 minus the 2 gives a 2, and then that's 2 minus a 9 gives a 3, and that's going to be negative kilojoules per mole. And what about delta HP2 major? It's going to be faster than minor. And we're breaking the same BRBR, that's positive 192. You're making a more exothermic CBR, negative 228. 8 minus 2, 6, 5. 8 minus 2, 6, and 2 minus 9 is 3, and it's a negative. Well, you know, tidy this up. Kilojoules per mole. Stay away from the trash can. There. Hey, negative 36 is faster than negative 32. That propagation step's faster. And guys, if you're worried about, how fast is the resonance happening? Resonance happens faster than you can even imagine. As soon as resonance is possible, it's starting to happen, and it's happening like millions of times per second. How's that? So if you need either resonance form, it's happening. The one that gives the better product is happening faster. Okay? So delta H reaction for the two reactions. Delta H RXN minor. I don't know how this is even happening. Why are you doing that? Don't do that. Minor equals negative 14 minus 32 equals negative 36 kJs per mole. Delta H reaction major. Uh-oh, did I do bad stuff? 46. Yeah, I don't know. How do you do that? That's just bad math. Just seriously bad math. Major. Same prop 1, negative 14. And different prop 2, negative 36. And that's not in the 40s anymore. Negative 50 kJs per mole. And we're about to do some splaining, as they say. But I'll let you soak that in first. We're supposed to explain why. Let's look at the question. Which of the two prop 2 steps will be faster? Explain. There we go. Well, we got the numbers to say this one, prop 2 is minor is negative 32. Prop 2 major is 36. This one's faster, but that's not going to get your point. You have to say more exothermic CBr bond happens faster. And you can only use that when delta S is roughly 0. We ignore entropy all the time, but we can't say that entropy is never important. You got to acknowledge entropy is important except here. That's what that says. When delta S is roughly 0, then we can, the Gibbs free energy thing had delta H minus T delta S. And the only reason we can use delta H to predict delta G is when delta S is 0. And you got to trust the teacher on this one. These reactions, delta S is virtually 0. Okay. So I guess that's the answer to B. And these were the answers to C. And I believe we are done.